Hello, and welcome to the Feeling Sleepy channel. I'm so glad you found your way here tonight. Perhaps you've had a long day. Perhaps your mind has been racing, filled with thoughts that won't quite settle. Or maybe you're simply the kind of person who finds peace in contemplating the vast mysteries of the universe, who prefers cosmic wonder to counting sheep. Whatever brought you here, you've made the right choice. Tonight, you have nothing to do but rest. Let your shoulders drop. Let your breathing slow and deepen. Feel your body growing heavy, as if gravity itself has softened its hold on you, allowing you to drift gently into the space between waking and dreaming. Because tonight, we're not simply stargazing. We're embarking on a quiet journey through our home galaxy, the Milky Way. A vast spiral of stars, dust, and mystery, turning slowly through space for over 13 billion years. Beneath its beauty lie secrets that still puzzle astronomers today. Rogue stars fleeing into darkness. Invisible forces holding everything together. Ancient stellar remnants older than the galaxy itself. We'll travel gently from its glowing spiral arms to its secretive, hidden core. From colossal collisions that happened billions of years ago, to stars being born right now in clouds of cosmic dust. You'll hear of black holes and stellar nurseries, of dwarf galaxies being torn apart, and of the strange, unfinished story of a galaxy still growing, still evolving, still becoming. Some of what you hear tonight may surprise you, some may answer questions you didn't know you had. But all of it is designed to give your mind something peaceful to rest upon as you drift into sleep. Let these cosmic truths wash over you like gentle waves, carrying you deeper into relaxation with each passing moment. And just before we begin, if these calm, curious explorations help you unwind, if they give you a quiet way to end your day, consider liking and subscribing to the Feeling Sleepy channel. It helps others find their way here too, others who are searching for peace in the vastness of knowledge, for rest in the comfort of cosmic perspective. Now, close your eyes if you haven't already. Take a deep breath in and out. Feel yourself becoming lighter, more at ease. And let's begin our journey through the Milky Way. The Milky Way is not a static photograph hanging in space. It is alive with motion, change, and transformation. Every star, every cloud of dust, every atom of gas is moving, orbiting, flowing through the darkness like currents in an invisible ocean. And you are part of this motion. Right now, as you rest, you are traveling through space at speeds that would seem impossible if you stop to think about them. But tonight, we won't think too hard. Tonight, we'll simply drift alongside these truths, letting them carry us gently towards sleep. Our solar system, the Sun and all its planets, including Earth, orbits the center of the Milky Way at more than 828,000 kilometers per hour. That's more than 230 kilometers every single second. Imagine that speed. And yet, despite this incredible velocity, it takes our solar system about 225 million years to complete just one loop around the galaxy. This immense circuit is called a galactic year. Think about that for a moment, but gently, without strain. In Earth time, in the brief span of human history, we've only circled the Milky Way about 20 times since our solar system first formed. When the very first dinosaurs appeared, wandering across ancient continents, we were in a completely different part of the galaxy. The stars our distant ancestors would have seen, had they been able to look up and understand, were not the same stars we see today. The constellations change, the neighborhood shifts, everything is in motion, and this motion continues even now, in the quiet of your room, in the stillness of this moment. The Earth turns beneath you. The Moon circles our planet. and the entire solar system sweeps forward through a galaxy that never stops moving, never stops changing, never stops becoming something new. The Milky Way may feel like a stable home, a permanent fixture in the universe, but it is built from wreckage. It is stitched together from the remnants of other galaxies, smaller systems that wandered too close and were absorbed, their stars scattered, their identities lost to the vastness of our own galactic spiral. Over billions of years, the Milky Way has consumed dozens, perhaps hundreds, of smaller galaxies. Each collision adds new stars, new gas, new material to the structure. These absorbed galaxies leave behind tidal streams, long ribbons of stars that wrap around the disk like gossamer threads, visible only to our most sensitive telescopes. One such galaxy, the Sagittarius dwarf, is being pulled apart right now, at this very moment. Slowly, inexorably, its stars are being stripped away, drawn into the Milky Way's gravitational embrace. In a few billion more years, it will be gone, completely dissolved, its stars indistinguishable from our own. And far off in the night sky, the Andromeda Galaxy is drifting slowly closer. This great spiral, similar in size and structure to our own, is on a collision course with the Milky Way. In about 4.5 billion years, the two galaxies will merge. It won't be violent, not in the way you might imagine. Stars are so far apart that they will almost never actually hit each other. But the shapes of both galaxies will change forever, their spiral arms stretching and distorting, their structures folding into something new and vast and quiet. Even galaxies are not eternal. They evolve. They collide. They die and are reborn in new forms. And in this transformation, in this constant change, there is something deeply peaceful. Nothing in the universe is permanent. Everything flows, shifts, becomes. And perhaps, in that knowledge, we can find permission to change too, to flow, to become whatever we need to be. Let that thought drift through your mind as you sink deeper into relaxation. Everything changes. Everything transforms. And that is not something to fear, but something to rest in. Here is something remarkable, something that bends our understanding of time and origin. Some stars in the Milky Way are older than the Milky Way itself. Let that statement settle for a moment. How can something be older than its home? How can the parts predate the whole? The answer lies in the galaxy's turbulent youth. Not every star in the Milky Way was born here. Some halo stars, ancient, metal-poor, and wandering in long, tilted orbits far above and below the galactic plane, appear to have formed even before the Milky Way had fully taken shape. Astronomers believe these stars may have originated in smaller, primordial galaxies that merged with our own billions of years ago. Their chemical fingerprints tell the story. These ancient stars contain almost no heavy elements, only hydrogen and helium. This suggests they were born shortly after the Big Bang, in a universe that had not yet had time to create the heavier elements we take for granted. Back then, there was no carbon, no oxygen, no iron. Just the simplest materials, still hot from creation, condensing into the first generation of stars. These elder stars move slowly and high above the galactic plane, like spirits from a time before spirals, before order, before structure. In their light, we see a universe that was younger, wilder, still learning to become what it is. They are witnesses to eras we can barely imagine, survivors of a cosmic youth that ended billions of years before our sun was even born. And they continue to shine, quietly, patiently, carrying their ancient light through the darkness. Although the Milky Way is ancient, it is not finished. Even now, even as you rest and your breathing slows, the galaxy continues to gather material. Gas flows in from the intergalactic medium, those vast empty spaces between galaxies. Stars are captured from dwarf galaxies that wander too close. Streams of dark matter, invisible and mysterious, feed the galaxy's enormous halo. The Milky Way grows not like a living thing, not with intention or purpose, but like a gravitational structure deepening over time. Some of this growth happens quietly, almost imperceptibly, as diffuse clouds of gas settle into the disk. Other times, growth comes with disruption. Satellite galaxies are torn apart by tidal forces, their stars scattered across the sky in long, graceful arcs. The galaxy you live in today is not the same galaxy the dinosaurs saw when they looked up at the night sky. And the galaxy your distant descendants may know, if there are descendants, if there is anyone left to look up in wonder, could be larger still, stitched together from the ruins of 1,000 smaller worlds. This is the nature of cosmic time. Change so slow, it seems like stillness. Growth so gradual, it appears static. But change, nonetheless, always, forever, without pause. Here's something surprising. We don't know exactly how many arms the Milky Way has. It seems like something we should know, doesn't it? How many major spiral arms curl out from the center of our own galaxy? But from our position deep inside the disk, it's remarkably hard to see the whole structure. Dust clouds obscure distant regions. Stars blur together. Distances are difficult to measure with precision. For decades, astronomers believed there were 4 major spiral arms. Then more recent observations suggested maybe fewer. Or perhaps that the arms twist and split in ways more complex than we expected. Some arms fade into fragments. Others wrap around in unexpected directions. The Milky Way may not be a neat pinwheel at all, but a living, layered swirl of stars shaped by forces we still don't fully understand. There's something comforting in this uncertainty, isn't there? In an age where we can access almost any information instantly, where we carry the sum of human knowledge in our pockets, there are still fundamental mysteries, still questions without answers, still things we don't know about the place we call home. Let that uncertainty be soothing rather than troubling. Let it remind you that not everything needs to be known or understood. Sometimes it's enough to simply exist within the mystery, to rest in the questions rather than grasping for answers. Most stars drift calmly through the galaxy, following their quiet orbits for billions of years. But a rare few are flung outward at astonishing, impossible speeds. Fast enough to escape the Milky Way entirely. These are hypervelocity stars, cosmic fugitives racing toward the edge of everything. Some of these rogue stars are remnants of binary systems disrupted by the supermassive black hole at the galaxy's center. Imagine 2 stars orbiting each other in an ancient dance, wandering too close to the galactic core. The black hole's immense gravity tears them apart. One star falls inward and vanishes beyond the event horizon, lost forever. The other is slung outward like a stone from a slingshot, hurled into the darkness at over 1 million kilometers per hour. These rogue stars travel alone, far from the galactic plane, like glowing comets with no return trajectory. They pierce through the outer halo and out into intergalactic space, into the vast emptiness between galaxies. They will wander forever through that darkness, isolated, solitary, carrying the light of the Milky Way with them into the void. They remind us that even in a galaxy bound by gravity, even in a system held together by invisible forces, there are moments of violent release. Quiet expulsions that send stars flying into the intergalactic night. Freedom, perhaps, or exile. It's hard to say which. High above the horizon, on certain dark nights, the Andromeda Galaxy appears as a faint blur to the naked eye. If you know where to look, if the conditions are right, you can see it. A spiral much like our own, lying over 2 million light-years away. And yet, it is moving steadily toward us, drawing closer with each passing moment. In about 4.5 billion years, the Milky Way and Andromeda will collide. But this collision won't be violent in any conventional sense. It won't be sudden or explosive. Stars are spaced so far apart that they will simply drift past each other, like ghosts passing through walls. Almost no stars will actually impact. The distances are too vast, the space is too empty. But gravity will warp both galaxies into long, stretching arcs. Tidal tails will curl outward into space, vast streams of stars pulled into new configurations. The central black holes of both galaxies may spiral together, eventually merging into a single, more massive object. And after billions of years of this slow, cosmic dance, the two galaxies will settle into a single, larger system. Some astronomers have already given this future galaxy a name, Milkomeda, or sometimes Milkdromeda. A new structure, neither fully Milky Way nor fully Andromeda, but something born from both. It will be a slow, elegant dance. The future of our home written across the stars. But don't worry. Don't let this trouble your rest. The sun will likely die long before this merger is complete. Humans, if they still exist in any form, will have faced and overcome countless other challenges by then. The collision of galaxies happens on timescales so vast that they become abstract, almost meaningless to the human mind. So let it be just another cosmic truth to drift past your consciousness as you sink deeper into sleep. Everything changes, everything merges, everything becomes something new. And that's okay. That's the way of things. Most stars in the Milky Way orbit the Galactic Center in the same general direction, following the overall rotation of the disk. But not all stars follow these rules. Some stars, especially in the outer halo, move in retrograde. They orbit backward, opposite to the galaxy's main rotation. These stars likely arrived from elsewhere, born in dwarf galaxies that were later absorbed by the Milky Way. Their reversed motion is a quiet signature of their foreign origin, a subtle marker that says, "I don't belong here, I came from somewhere else." It's as if the galaxy carries old memories in motion. Stories of ancient mergers and cosmic encounters, preserved not in light or matter, but in the slow, patient turning of stars against the stream. These backward-moving stars are living archives, their orbits encoding the galaxy's turbulent past. And there's something poetic in that, isn't there? The idea that motion itself can be memory. That the way something moves can tell you where it came from, what it's been through, how it came to be here. Perhaps we're not so different. Perhaps our own movements, our habits, our patterns, encode our histories in ways we don't fully recognize. But tonight, we're not analyzing. We're simply observing. Simply drifting alongside these truths as they float past. Over billions of years, the Milky Way has not grown alone. It has consumed. Small galaxies, faint dwarf companions, have drifted too close, been caught in the Milky Way's gravity, and slowly dismantled. Their stars are now part of our halo, our disk, woven into stellar streams that trace old orbits through space. Astronomers have identified several of these ancient mergers by analyzing the motion and composition of stars. One especially significant event has been called the Gaia-Enceladus merger. About 10 billion years ago, a dwarf galaxy roughly a quarter of the Milky Way's mass collided with our galaxy. This wasn't a gentle absorption. It was violent enough to reshape the early structure of the Milky Way, adding billions of stars and fundamentally altering the galaxy's evolution. Evidence of this ancient collision is everywhere once you know how to look. Certain populations of stars in the halo all move together, following similar orbits, sharing similar compositions. They are the remnants of Gaia Enceladus, the scattered survivors of a galaxy that no longer exists. The Milky Way is not a pristine spiral, never has been. It is a composite, built from quiet collisions, stitched together from the remains of many smaller worlds. And perhaps there's wisdom in that structure. Perhaps the most beautiful, complex things in the universe are not pure or simple, but composite. Made from many parts, many histories, many stories woven together into something greater than any individual component. Every star carries a unique chemical fingerprint, a pattern of elements imprinted at birth that remains throughout its life. By studying these signatures, astronomers can trace a star's history, determine where it was born, and sometimes even identify stars that came from the same original cloud of gas. Some stars are rich in heavy elements like iron, carbon, and calcium. These are called metal-rich stars, though to an astronomer, any element heavier than helium counts as a metal. These stars formed in dense regions where previous generations of stars had already lived, died, and scattered their enriched material back into space. Other stars are nearly pure hydrogen and helium, born when the universe was still young, before many heavy elements had been created. These metal-poor stars formed in an earlier, simpler cosmos, and their composition reflects that primordial purity. By studying these differences, astronomers can group stars into families, uncover evidence of ancient mergers, and reconstruct the hidden story of the Milky Way's formation. In this way, chemistry becomes a kind of time machine, letting us read a star's past like lines of ancient poetry written in light. And there's something deeply satisfying about that. The idea that everything carries its history within itself. That you can read the past in the present if you know what to look for, if you understand the language. Stars tell their stories through their light, through the specific wavelengths they emit and absorb. And patient observers, humans with telescopes and spectrographs, can read those stories written in atoms and photons. Across the sky, though invisible to the naked eye, thin ribbons of stars stretch in arcs and curves. These are stellar streams, the remnants of smaller galaxies that wandered too close to the Milky Way and were pulled apart by tidal forces. As these doomed dwarf galaxies orbit the Milky Way, their stars are gradually stripped away and smeared across space, forming long, delicate trails that trace their former paths. Some streams wrap around the galaxy like ghostly halos. Others dive inward toward the core. Each one tells a story of destruction and absorption, of a small galaxy's final journey before dissolving into the larger structure. These streams are evidence of past collisions, quiet mergers that built the Milky Way over billions of years. The galaxy, like a tree, carries the rings of its past in every thread of light, in every arc of stars scattered across the halo. Finding these streams requires careful observation and sophisticated analysis. They're faint, diffuse, easily lost in the foreground of brighter stars. But modern telescopes and surveys have revealed dozens of them, each one a fossil of galactic consumption, each one a memory written in motion. Our galaxy doesn't lie flat like a perfect spiral in a textbook diagram. The Milky Way's disk bends and curves, warped like a vinyl record left too long in the sun. The disk tilts upward on one side and downward on the other, forming a graceful wave across the stars. This subtle warp was invisible to us until radio telescopes mapped the hydrogen gas that stretches far beyond the visible starlight. Once astronomers could see, in radio wavelengths, the warp became obvious, unmistakable. What causes this distortion? Astronomers believe several factors contribute. Satellite galaxies like the Magellanic Clouds tug gently on the Milky Way's edges. Clumps of dark matter bend the structure from below. The galaxy's own rotation creates instabilities that ripple through the disk. All of these forces combine to create a shape that's more complex than a simple flat plane. Like ripples in a great spinning sheet, the warp reveals that galaxies are never fully still. Over time, they bend, flex, and change form in response to invisible forces. From a distance, the Milky Way might look like it's dancing slowly through space, its edges undulating in a rhythm too slow for human perception, but very real nonetheless. And there's something beautiful in this imperfection. The Milky Way is not a perfect spiral. It's warped, lopsided, asymmetric. And that's what makes it real, makes it complex, makes it interesting. Perfection is sterile. But imperfection, irregularity, asymmetry, that's where character lives. You can only see about 0.00003% of the Milky Way with the naked eye. Let that number sink in for a moment. Under the clearest, darkest sky, far from cities and streetlights, you might see a few thousand stars. To the human eye, that seems like an ocean of light, an overwhelming abundance of stellar brilliance. But it's barely a droplet in the cosmic ocean. The Milky Way contains over 100 billion stars. Some estimates put the number closer to 400 billion. Most are hidden from view. Some lie behind thick curtains of interstellar dust. Others are too faint or too far away for our vision to reach. Many are red dwarfs, so dim that even nearby ones are invisible without a telescope. The pale streak of the Milky Way that crosses the sky on moonless nights is just the innermost whisper of the whole structure. We live surrounded by a colossal river of starlight, immersed in it, part of it, and yet almost all of it remains invisible to us. Too vast to grasp from within, too large to comprehend in its entirety. And maybe that's okay. Maybe we're not meant to see everything. Maybe the small portion we can see is enough to inspire wonder, enough to make us feel connected to something larger than ourselves. The invisible majority can remain mysterious, unknown, waiting patiently in the darkness for future generations with better tools and deeper understanding. Unlike planets in a solar system, which follow neat, predictable tracks around their star, stars in the Milky Way move with more freedom and complexity. Some race ahead in the inner regions, orbiting the Galactic Center in just a few million years. Others drift slowly along the outskirts, taking hundreds of millions of years to complete a single loop. This difference in orbital speed is actually what creates and maintains the spiral arms. The arms aren't solid structures, rigid features carved into the galaxy. Instead, they're patterns, density waves moving through the disk like slow traffic jams in space. Imagine a highway where cars bunch up at certain points, creating regions of higher density that move along the road. Individual cars enter these traffic jams, slow down for a while, then exit and speed up again. But the traffic jam itself moves at a different speed than any individual car. That's essentially what spiral arms are. Regions of slightly higher density that rotate through the disk at their own rate. As stars and gas clouds pass through these density waves, they're compressed. This compression triggers the collapse of gas clouds and the birth of new stars. The newly formed, bright blue stars light up the arms in curls of brilliant white and blue light, making the spiral pattern visible. By the time these stars drift out the other side of the density wave, they've aged, dimmed, and become less prominent. Our own sun is part of this swirl, moving in and out of these patterns across cosmic time. The galaxy is not a clock, ticking in perfect regularity. It's a current, a flow, and we are drifting in it, carried along by forces too large and slow to perceive directly. The galaxy holds together because of something we cannot see, something we don't fully understand, something that challenges everything we thought we knew about matter and gravity. By all logic, based on what we can directly measure, the Milky Way should not exist. If we count up all the stars, all the gas, all the dust, all the visible matter in the galaxy, there isn't enough mass to account for how fast the outer edges are spinning. Those distant stars should be flung into space, scattered like leaves in a storm. And yet they remain, held in stable orbits by some invisible force. The answer, astronomers believe, is dark matter. This mysterious substance does not shine, does not reflect light, does not emit any electromagnetic radiation that we can detect. But it exerts gravity, and there is so much of it that it outweighs all the visible matter in the galaxy many times over. We don't know what dark matter is. It might be exotic particles that barely interact with normal matter. It might be something even stranger, something that requires new physics to explain. But we know that without it, without this invisible scaffolding, the Milky Way would fly apart. Dark matter is what holds everything in place, a ghost structure supporting the galaxy we see. And there's something humbling in this mystery, isn't there? The idea that most of the universe is made of something we can't see, can't touch, can't detect except through its gravitational effects. We live in a cosmos where the majority of matter is invisible to us, where the foundations of galaxies are built from something unknown. Let that thought be calming rather than troubling. Let it remind you that mystery is not a problem to be solved, but a truth to be accepted. Some things remain unknown, and that's perfectly fine. At the very center of the Milky Way lies an enormous black hole, a singular point of gravity so intense that not even light can escape it. This object is called Sagittarius A, and it is more than 4 million times the mass of our Sun. Yet, despite this incredible mass, it occupies a space smaller than the orbit of Mercury. All of that matter, all of that gravity, compressed into a region so small that it would fit comfortably within our inner solar system. It's difficult to wrap your mind around, difficult to comprehend something so massive yet so compact. We cannot see Sagittarius A directly. By definition, black holes don't emit light. But we've watched nearby stars whip around it at tremendous speeds, tracing invisible loops through the void. These stars move so fast that they complete full orbits in just years or decades, their motion clearly revealing the presence of something massive and invisible at the center. Sometimes gas and dust fall inward toward the black hole, pulled by its overwhelming gravity. As this material spirals inward, it heats up, accelerates, and flares with X-rays and radio waves. These brief outbursts give us glimpses of the black hole's edge, the point of no return called the event horizon. For now, Sagittarius sleeps. It's relatively quiet compared to the supermassive black holes in other galaxies. But long ago, it may have burned like a quasar, actively feeding on vast amounts of infalling matter and lighting up the galaxy from within with brilliant, violent radiation. It is the silent conductor at the Milky Way's heart, pulling nearby stars into a slow, relentless dance. A cosmic singularity hiding in plain sight, invisible, yet undeniable. When astronomers mapped the center of the galaxy in detail, they discovered something unexpected. The central bulge is not a smooth, round ball of stars, as you might expect. Instead, it has a strange, three-dimensional shape. Seen from the side, it resembles a peanut or an hourglass. The bulge swells in the middle and narrows at the ends, creating this distinctive shape. This geometry likely formed from the galaxy's central bar, a dense stripe of stars that rotate slowly through the core. Over billions of years, this bar has buckled and puffed upward, creating vertical structure. These inner regions are sculpted by complex gravitational dynamics, billions of years of stellar orbits, and the accumulated rhythm of the galaxy's rotation. We live in a spiral galaxy, but its heart is full of complexity. Not flat or simple or clean, but intricate and alive, shaped by forces acting over timescales we can barely comprehend. The discovery of this shape required looking at the galaxy in infrared light, which can penetrate the dust that obscures the center in visible wavelengths. When astronomers finally saw through the dust, they found not the simple structure they expected, but something far more interesting and strange. The Milky Way's spiral arms are not simply made of stars. They're woven from the birthplaces of stars, vast clouds where new suns are being born even now, even as you rest. Giant clouds of hydrogen, dust, and molecules drift through the galaxy, some spanning hundreds of light years across. When these clouds pass through the spiral arms, they're compressed by the density wave. This compression causes them to collapse under their own gravity, fragmenting into smaller clumps. Within these clumps, matter continues to fall inward, growing denser and hotter. Eventually, the pressure and temperature at the center become intense enough to ignite nuclear fusion, and a star is born. The process takes millions of years from start to finish, but the result is a newborn sun, blazing with the light of fusion, pushing back against gravity with the energy of nuclear fire. These regions are called stellar nurseries, and they're chaotic, glowing, and full of motion. Ultraviolet light from the hottest new stars lights up the surrounding gas, painting the arms with radiant blues and silvers. These bursts of creation trace out the spiral shape, illuminating the curves of the galaxy with quiet fire. Every star, even our sun, was born from one of these cloudy cradles long ago. 4.5 billion years in the past, in some forgotten stellar nursery, the sun ignited for the first time. And now it's middle-aged, stable, quietly burning as it has for billions of years, as it will for billions more. Beyond the flat spiral disk lies something far more diffuse, far more mysterious. A spherical halo that surrounds the entire galaxy, extending far out into space. This halo contains ancient stars, globular clusters, and enormous amounts of dark matter. Though it appears nearly empty, nearly invisible, this halo may hold the majority of the Milky Way's mass. Its stars are spread thin across vast distances, orbiting in long, slow arcs that rarely touch the disk. The halo also preserves the remnants of ancient galactic mergers. Streams and shells of stars, torn from smaller galaxies, are left behind like cosmic fossils, embedded in the halo's structure. These tidal remnants can persist for billions of years, slowly dispersing but never quite disappearing. It is the galaxy's outer memory, quiet and dim, but still in motion, still shaping what the Milky Way becomes. While the disk is bright and active, full of young stars and ongoing star formation, the halo is ancient, serene, populated by the ghosts of long-dead galaxies. If you could somehow step outside the Milky Way and look at it from a great distance, you would see the bright disk first. That's what draws the eye, what appears in photographs and illustrations. But surrounding that disk, extending far into the darkness, you would see a faint spherical glow. That's the halo, subtle but vast, containing more volume and more mass than the visible galaxy itself. Scattered throughout the halo are globular clusters, among the oldest objects in the galaxy. These are compact spheres made of hundreds of thousands of tightly bound stars, so densely packed that near the center, stars are separated by distances measured in light, weeks rather than light years. Globular clusters orbit the galactic center in the halo, like moths circling a distant flame. They follow long, elliptical paths that take them far above and below the disk, then sweep them back down through the plane before carrying them up again on the other side. These clusters are incredibly stable. Some are more than 12 billion years old, nearly as old as the universe itself. Many contain stars that predate the Milky Way's formation, stars that were born in smaller galaxies later absorbed by our own. The stars in globular clusters are metal poor, meaning they formed before the universe had time to create many heavier elements. Each generation of stars enriches the cosmos with new elements forged in stellar cores and scattered by supernovas. But the stars in globular clusters were born early in this process, when only hydrogen and helium were abundant. They serve as time capsules, holding clues to how the galaxy formed, what it consumed, and what conditions were like in the early cosmos. These quiet, golden spheres drift patiently through the halo, glowing in the dark, ancient witnesses to billions of years of cosmic history. Long ago, the Milky Way was more active, more vibrant, bursting with fresh stars born from dense, collapsing clouds. The galaxy was younger then, and there was more gas available, more fuel for star formation. But in recent cosmic epochs, the pace has slowed significantly. There is still gas available throughout the galaxy, but much of it is spread thin, heated by stellar radiation and supernovas, or locked in forms that resist collapse. The conditions that trigger star formation are less common now than they were billions of years ago. The galaxy is not done making stars. Star formation continues, especially in the spiral arms and in certain dense molecular clouds. But the rate has declined. Astronomers estimate that star formation peaked several billion years ago and has been steadily declining ever since. This doesn't mean the end is near, only that we live in a quieter chapter of galactic history. The Milky Way is a mature spiral now, glowing gently in its middle age, still forming stars but no longer in a hurry. The frantic youth has passed, replaced by a more measured, steady pace. And there's something appropriate in that, isn't there? Everything has its season, its time of youth and vigor, and its time of maturity and calm. The galaxy, like all things, is aging. And in that aging, there is not loss but transformation. The disk, the broad, flat spiral we think of as the Milky Way, formed gradually over time. But some of the stars in our galaxy are older than the disk itself. These ancient stars reside mostly in the halo, or the thick disk, and they formed when the galaxy was still assembling. Back then, the Milky Way was not yet a spiral. It was a loose cloud of stars, gas, and dark matter, slowly collapsing inward under its own gravity. By studying the composition and motion of these pre-disk stars, astronomers can peer back into the era before structure, before the spiral arms formed, before the galaxy settled into its current configuration. These stars are the elders of the galaxy, silent witnesses to its birth and the long, slow shaping of what we now call home. They remember a time before the Milky Way looked like it does today, a time when the galaxy was formless, chaotic, still becoming. These stars drift through the thick disk and halo, following orbits that don't quite match the neat circular paths of younger stars. Their trajectories are tilted, eccentric, carrying the memory of the galaxy's turbulent assembly in their motion. When you look at one of these ancient stars, you're seeing light that left its surface traveling for decades, centuries, or millennia to reach your eyes. But that light comes from a star that has been burning for over 10 billion years, a star that was already ancient when our solar system was born. A galactic year is about 225 to 250 million Earth years. This is the time it takes for the Sun to complete one full orbit around the center of the Milky Way. It's a vast cycle of motion that dwarfs all our calendars, all our concepts of time. In the time it takes for the Sun to circle the galaxy once, continents drift, mountain ranges rise and erode, species evolve and go extinct, entire epochs unfold and conclude. Astronomers estimate we are currently about halfway through one such orbit. The last time the solar system was in this part of its path around the galaxy, the supercontinent Pangaea had just begun to break apart. Dinosaurs had not yet emerged. The world was ruled by early reptiles and amphibians. The landscape, the climate, the very biology of Earth was unrecognizably different. A galactic year is the slow heartbeat of cosmic time, a rhythm too vast for human minds to fully grasp, but real nonetheless. The Sun has completed fewer than 25 of these immense orbits in all its 4.6 billion years of existence. That's fewer than you might expect, considering the Sun's incredible speed through space. We often think of the stars as ancient and unmoving, eternal and fixed. But our solar system is still young on a galactic scale, a newcomer in a city of older, more traveled suns. We are part of the galaxy's motion, but still early in its long, winding story. According to Newtonian physics, according to everything we understand about gravity and orbital mechanics, stars farther from the galactic center should orbit more slowly. Just as outer planets in our solar system move more leisurely around the Sun, distant stars should take their time circling the galaxy. But point in the Milky Way, stars in the outer regions orbit almost as quickly as those near the center. This defies classical expectations. It shouldn't happen. The numbers don't work out unless there's more mass present than we can see. The reason, astronomers believe, is dark matter. That invisible, unknown form of mass that surrounds the galaxy in a vast halo provides the extra gravitational pull needed to keep the outer stars moving at their observed speeds. Without dark matter, the galaxy would not hold together. With it, the math works. The observations make sense. The Milky Way turns almost like a solid wheel, not because we understand it fully, but because something unseen is holding it in place, binding it together with gravity we can measure but cannot explain. And once again, we encounter mystery. Once again, we find that the universe is not as simple or straightforward as we might hope. There are forces at work beyond our direct perception, structures built from matter we cannot see. And that's okay. That's just the nature of reality. Complex, layered, full of unknowns. Scattered throughout the Milky Way are vast, dark clouds of cold gas. These molecular clouds, composed mostly of hydrogen molecules and traces of dust, can span hundreds of light years across. Within their cold, dense interiors, which can be just a few degrees above absolute zero, gravity begins to work. Matter slowly gathers, forming clumps that eventually collapse into new stars and planets. These clouds are the galaxy's wombs, quiet, hidden places where the future begins in silence. Some of these clouds are so large and so cold that they absorb visible light entirely, appearing as black patches against the starry sky. They're called dark nebulae, and they were once mistaken for empty regions of space, holes in the heavens. But they're not empty at all. They're full of matter, full of potential, pregnant with stars waiting to be born. The most famous of these is perhaps the Horsehead Nebula, a dark cloud silhouetted against glowing gas, shaped like the head and neck of a horse. Or the Coalsack Nebula, a prominent dark patch visible in the southern sky. These aren't voids but veils, curtains of shadow drawn across the stage of star formation. When massive stars reach the end of their lives, when they've exhausted all their nuclear fuel, they don't die quietly. They explode in cataclysmic supernovas, events so powerful they can outshine entire galaxies for a brief moment. These explosions don't just end stellar lives, they create. They transform. Shock waves from supernovas ripple through the interstellar medium, compressing nearby clouds and triggering new waves of star formation. The explosion's energy can travel for light years, pushing into surrounding gas, creating shells and bubbles, initiating the collapse that will eventually birth new stars. Supernovas also enrich the surrounding space with heavy elements forged in the dying star's core. Iron and gold, carbon and oxygen, all the elements heavier than helium, are created in stellar cores and scattered by these explosions. Every atom of iron in your blood, every atom of calcium in your bones, was created in the heart of a star and scattered into space by a supernova explosion billions of years ago. In this way, supernovas act like storms within the galactic ecosystem. They stir, they fertilize, they reshape everything around them. They are moments of chaos, destructive and radiant, and absolutely necessary. Without supernovas, there would be no heavy elements. Without heavy elements, there would be no rocky planets, no chemistry complex enough for life. Destruction and creation, intimately linked, inseparable. The Milky Way is full of light we cannot see. Interstellar dust, made of microscopic grains of carbon, silicon, and ice, weaves through the galaxy in clouds and tendrils. In visible light, this dust obscures vast regions of space, blotting out stars and entire nebulae. But behind this veil, star formation continues. Infrared telescopes can peer through the dust, revealing glittering nurseries filled with newborn suns. What looks like darkness in visible light is often revealed as brilliant activity when viewed in infrared. The dust, though it hides so much from us, is actually part of the star formation process. It absorbs energy from nearby stars, helping gas clouds cool. It shields the delicate early stages of stellar birth from harsh radiation. It provides surfaces where molecules can form, enabling complex chemistry that wouldn't be possible in pure gas. What seems like emptiness is often the beginning of something bright. What appears to be obstruction is often protection, enabling creation rather than preventing it. Not every cloud of gas becomes a star. Across the Milky Way, astronomers have found massive cold clouds that seem destined for collapse, yet remain dark and dormant. Some are too diffuse, spread too thin for gravity to overwhelm the pressure that resists collapse. Others may be stabilized by magnetic fields threading through them, or by internal turbulence that prevents any region from condensing enough to ignite. These starless clouds float through the galaxy like silent possibilities, rich in molecular hydrogen but untouched by fusion. They may one day ignite if disturbed by a passing shock wave or the gravity of a nearby star. or they may drift until torn apart by external forces, their gas recycled into other regions. In these clouds, the galaxy holds its breath, waiting, perhaps, for the right nudge to spark something new. Or perhaps simply existing. Not every cloud needs to become a star. Not every potential needs to be realized. Some things can simply be, drifting quietly through space, part of the ecosystem without needing to transform. There's permission in that, isn't there? The permission to simply exist without constantly becoming, without always transforming. Some clouds remain clouds, and that's enough. Stars are not permanent. They live, burn, and die. And in dying, they return their material to the galaxy, completing a cycle that has repeated countless times over billions of years. Supernovas spread heavy elements across light years. Red giants, nearing the end of their lives, shed their outer layers into space. Planetary nebulae, those beautiful shells of glowing gas, drift outward, carrying enriched material back into the interstellar medium. This enriched material joins the vast ocean of gas and dust between stars. There it cools, mixes, condenses, and eventually forms new stars, new planets, new systems. And the cycle continues, generation after generation, each one building on the last. Every atom in your body has passed through this cycle multiple times. The iron in your blood was forged in a star that died before the sun was born. The calcium in your bones was created in a supernova explosion and scattered into space. The oxygen you breathe with every breath was produced by nuclear fusion in stellar cores. Born in a star, scattered into space, gathered into a new cloud, incorporated into a new star system, eventually finding its way to Earth, to your body, where it serves a temporary role in the brief spark of consciousness that is your life. And when you die, when Earth itself eventually dies, those atoms will be released again, returned to space, free to join the next cycle. The Milky Way is not a static stage, but great engine of renewal. It breathes in time with its stars, making, unmaking, and beginning again. Nothing is lost. Everything transforms. The cycle continues forever. In astronomy, metals are not just iron or gold. They are any elements heavier than helium. Hydrogen and helium are called primordial because they were created in the Big Bang. Everything else, every other element, is called a metal and was created in stars. The earliest stars in the universe had almost no metals because they formed before earlier generations of stars had a chance to forge and scatter these elements. The universe started with only hydrogen and helium. It took time, generations of stars, to build up the heavier elements. Today, astronomers seek out metal-poor stars in the halo of the Milky Way. These stars, faint and ancient, preserve the chemical conditions of a time long gone. By analyzing their composition with spectrographs that split their light into component wavelengths, we compare into the primordial past. We can see what the universe was like shortly after the Big Bang, before galaxies had matured, before the periodic table had filled in. These stars are fossils made of light, living relics from the dawn of creation. Some of these metal-poor stars contain less than 1/10,000th the iron found in the Sun. They are incredibly pure, incredibly ancient, carrying within them the memory of a simpler, younger cosmos. A star's birthplace doesn't always define its destiny. Over time, many stars drift away from their natal clouds, displaced by gravitational interactions, orbital resonance, or the slow pull of the spiral arms. Some stars are ejected at high speeds, flung across the disk or into the halo by close encounters with other stars, or by the slingshot effect of passing through dense regions. Others migrate gradually, shifting their orbits inward or outward as they spiral through the galaxy over billions of years. Even our Sun is not where it began. When the Sun first ignited, 4.6 billion years ago, it was in a different part of the galaxy, surrounded by different stars. It has migrated since then, slowly drifting to its current position in what we call the Orion Spur. Tracing the paths of stars reveals a Milky Way that is anything but static. It's a galaxy alive with movement, exchange, and quiet dislocation. Home for a star may only be temporary. The neighborhood changes, the surroundings shift, everything drifts. And perhaps we can find comfort in that. Perhaps the impermanence of place, the constant drift and change, is not something to resist, but something to accept. We are all migrants through space and time, temporary residents in an ever-changing cosmic landscape. Just as Earth orbits in a Goldilocks zone around the Sun, not too hot and not too cold for liquid water and life, the Milky Way may have its own galactic habitable zone. This region is thought to lie between two extremes. Too close to the galactic center, and the environment becomes dangerous. High stellar density means more frequent supernova explosions, more intense radiation, more gravitational disturbances. The central regions are chaotic, violent, inhospitable. Too far from the center, in the sparse outer edges of the galaxy, conditions are different but perhaps equally challenging. Star density is low, which means fewer supernova disturbances, but also the planetary systems may be metal poor, lacking the heavy elements needed to form rocky planets and complex chemistry. Somewhere in between lies a wide band where conditions are just right. The Galactic Habitable Zone, sometimes called the Galactic Goldilocks Zone. Here, stellar density is moderate, supernovas are not too frequent, radiation levels are manageable, and elements like carbon, oxygen, and iron are abundant. Earth lies within this zone, orbiting a quiet star in a relatively stable neighborhood of the galaxy. And this might not be a coincidence. If life requires certain conditions, certain balances, then perhaps it naturally arises in regions where those conditions exist. We might not be alone in finding a foothold here. Other civilizations, other forms of life, might have emerged in similar circumstances throughout this habitable band. Or perhaps not. Perhaps we are unique, a singular spark in an otherwise dark galaxy. We don't know yet. But the conditions that allowed life to develop on Earth exist across a huge swath of the Milky Way. Our solar system doesn't lie in one of the Milky Way's grand spiral arms. Instead, we occupy a small structure called the Orion Spur, also called the Orion Arm or the local spur. It's a relatively quiet lane of stars nestled between the larger Sagittarius and Perseus arms. It's not especially dense with stars, not especially active with star formation. And that may be exactly why we're here. In the calm between galactic highways, massive supernovas are rarer. Radiation storms are less frequent. The gravitational environment is more stable. This quiet corner may have given life on Earth the time it needed to emerge and evolve. Life requires stability, requires a certain amount of cosmic peace. Too much activity, too many disturbances, and complex life might never have the chance to develop. From the outside, the galaxy seems dramatic and radiant. The spiral arms blaze with newborn stars. The center glows with ancient stellar populations. But here in this quiet spur, in this unassuming neighborhood, we found just enough peace for complexity to unfold, for intelligence to emerge, for consciousness to wonder about its place in the cosmos. Sometimes the most interesting things happen not in the dramatic center, but in the quiet margins. In the Milky Way, the spiral arms rotate at a different speed than individual stars. The arms are patterns, density waves, and they move at their own rate through the disk. But there is a special distance from the center called the co-rotation radius, where the average speed of stars matches the rotation speed of the spiral arms themselves. At this location, stars and spiral arms move together, in sync. Earth's sun orbits close to this boundary. We're near the co-rotation radius. This gentle match in motion may help us avoid frequent crossings of spiral arms, places with higher star density, more supernovas, more gravitational disturbances. Every time a star crosses through a spiral arm, it experiences compression, increased stellar encounters, and exposure to more intense radiation from massive young stars. These crossings might disrupt planetary systems, trigger comet impacts, or bathe planets in harmful radiation. By orbiting near the co-rotation radius, the Sun minimizes these crossings. We drift gently alongside the spiral pattern rather than plunging through it repeatedly. We live, quite possibly, in one of the more stable neighborhoods of the galaxy, protected not by walls or barriers, but by resonance, by gentle synchronization with the galaxy's grand pattern. As it orbits the Milky Way, the Sun doesn't follow a perfectly flat path. Instead, it moves in a gentle wave, drifting above and below the galactic plane like a cork bobbing in slow motion. This vertical oscillation happens over tens of millions of years. The Sun rises above the plane, reaches a maximum height, falls back down, crosses through the plane, continues downward to a maximum depth, then rises again. The full cycle takes about 60 to 70 million years. This motion is caused by the gravitational tug of the galaxy's mass distribution. The disk itself has gravity that pulls objects toward it. When the Sun drifts above the plane, it's pulled back. When it falls below, it's pulled up. The result is a gentle oscillation, a cosmic sine wave traced through space over geological timescales. Some researchers have wondered whether this motion might influence cycles of extinction on Earth. Perhaps passing through the galactic plane exposes us to more cosmic rays, more cometary impacts, more disturbances. The evidence is not yet clear, and the hypothesis remains speculative. But regardless of whether it affects life on Earth, it's a reminder that even on its steady path around the center, the Sun is not simply gliding smoothly. It's swaying, oscillating, tracing a complex three-dimensional path through the galaxy. Nothing moves in straight lines. Everything curves, spirals, waves through space. Dark matter makes up most of the Milky Way's mass, yet it has never been seen directly, never been touched, never been detected, except through its gravitational effects. It does not emit light. It does not absorb light. It does not reflect light. As far as we can tell, it passes through ordinary matter as if it weren't there, interacting only through gravity. You could hold a lump of dark matter in your hand, if such a thing were possible, and you would feel nothing, see nothing, detect nothing except its weight. But its gravitational effects are unmistakable, undeniable. Dark matter holds the galaxy together. It explains the unexpected rotation speeds of stars. It shapes the formation of large-scale cosmic structures. Without it, galaxies as we know them could not exist. Astronomers detect dark matter not by seeing it, but by watching how it moves other things. Stars orbit too fast. Galaxies cluster in ways that require more mass than we can see. Gravitational lensing, the bending of light around massive objects, reveals invisible mass that must be there even though we can't observe it directly. Dark matter is the galaxy's hidden scaffolding, invisible, silent, and still one of the greatest mysteries in science. We know it exists. We can measure its effects. But we don't know what it is, what it's made of, why it behaves the way it does. And there's something profound in this ignorance. The majority of the universe is made of something we don't understand. Most of reality is invisible to us, beyond our direct perception. We live in a cosmos that is fundamentally mysterious, fundamentally unknown. Let that be humbling rather than frightening. Let it remind you that human knowledge, vast as it has become, is still finite, still limited, still surrounded by unknowns. Most of the Milky Way's visible stars lie within the flat, luminous disk. But the majority of its mass resides elsewhere, in an enormous dark matter, halo extending far beyond the furthest stars. This halo holds the galaxy together, outweighing the visible disk by a large margin. It's populated sparsely with ancient stars and globular clusters, but its true bulk is unseen, made of dark matter distributed in a roughly spherical cloud. When we think of the Milky Way, we picture its spiral arms and starry plane. That's the part we can see, the part that appears in photographs and illustrations. But that's only the glowing surface, only the visible tip. The mass that defines the galaxy, its gravity, its motion, its reach into surrounding space, is mostly hidden. The galaxy is like an iceberg. What we see is the small fraction above water. The vast bulk remains submerged, invisible, supporting the visible structure from below. This hidden mass shapes everything. It determines how far stars orbit. It controls the galaxy's interaction with neighbors. It will influence the eventual merger with Andromeda billions of years from now. The invisible majority governs the visible minority. You might think we would know the mass of our own galaxy with precision. We live here, after all. We've studied it for centuries. Surely we can count up everything and arrive at a definite number. But measuring the Milky Way's mass is remarkably difficult. Stars and gas make up only a small portion of the total. The rest lies in the vast dark matter halo, which we cannot see directly. Estimates vary widely. Some suggest a mass close to 1 trillion times that of the Sun. Others place it significantly higher, perhaps 1.5 trillion solar masses or even more. The uncertainty comes from trying to measure how far stars and satellite galaxies orbit at great distances, a task clouded by limited data and the influence of invisible matter. We can measure the speed of nearby stars with great precision. But the farther out we look, the harder it becomes. Distant stars are faint, difficult to track. Their motions are harder to measure accurately. And yet those distant orbits are exactly what we need to weigh the galaxy as a whole. The Milky Way is our home, the galaxy we've studied most intensely. And yet its weight, its total mass, remains somewhat uncertain. We know the approximate range, but not the exact value. There's something both frustrating and fascinating about this. Even basic facts about our cosmic address remain slightly fuzzy, slightly uncertain, still being refined. For many years, astronomers assumed that the Andromeda Galaxy, which appears slightly larger and brighter than the Milky Way in photographs, was also more massive. The bigger, more luminous sibling to our own galaxy. But recent measurements suggest that the Milky Way's dark matter halo may be broader and denser than previously believed. If that's true, our galaxy could actually outweigh Andromeda, despite its more modest appearance in visible light. This matters not only for comparisons and for understanding galactic formation, but also for predictions. When the two galaxies eventually merge in about 4.5 billion years, their relative masses will shape the encounter's dynamics, will determine the final structure of the merged system. If the Milky Way is more massive, it will play a larger role in shaping the merger. The combined galaxy might retain more characteristics of the Milky Way than of Andromeda. Or perhaps the two are similar enough in mass that the merger will be a true blending, neither galaxy dominating. We won't know for certain until we refine our mass estimates, but it's intriguing to consider that the Milky Way, which appears smaller and less prominent, might actually be the heavier of the two. Appearances can be deceiving. The invisible often outweighs the visible. The large and small Magellanic Clouds, two bright satellite galaxies visible from the southern hemisphere, have long been thought to orbit the Milky Way in long-standing companionship. But new evidence suggests they may be newcomers, captured only recently in cosmic terms. Their velocity and motion through space hint that this could be their first close pass by the Milky Way, not the latest in a long series of orbits. If true, they're not ancient companions, but distant wanderers just now, falling under the Milky Way's gravitational pull. Their arrival has had noticeable effects. They've stirred the outer disk, contributing to its warp. They've pulled on the galaxy's structure, creating asymmetries and disturbances. The Magellanic Clouds are irregular dwarf galaxies, lacking the grand spiral structure of the Milky Way, but nonetheless containing billions of stars and active star formation. They're large enough and close enough to be visible to the naked eye from southern latitudes, appearing as hazy patches of light. For thousands of years, people in the southern hemisphere have looked up at these clouds without understanding what they were. Now we know they're separate galaxies, gravitationally interacting with our own, possibly on their first approach, possibly about to be absorbed and destroyed like so many dwarf galaxies before them. The sky is quiet but full of first encounters, full of meetings and mergers, happening so slowly they seem like stillness. Trailing behind the Magellanic Clouds is a vast ribbon of hydrogen gas, a structure called the Magellanic Stream. It stretches over hundreds of thousands of light years, wrapped in curves and arcs across the southern sky. This stream was pulled away by tidal forces. As the Magellanic Clouds pass close to one another and to the Milky Way, gravitational interactions stripped gas from their outer regions. This gas now traces the cloud's path through space, a long trailing whisper of motion and loss. The stream is invisible in ordinary light. It doesn't contain stars, only diffuse hydrogen gas. But radio telescopes can map it, can see its structure and trace its origin back to the Magellanic Clouds. This gas may one day feed new star formation in the Milky Way. It may settle into the disk, condense into clouds, and eventually form new stars, new systems. Material from one galaxy becoming part of another. The boundary between us and them blurring, fading, eventually disappearing. Or the gas may simply settle into the halo, becoming part of the galaxy's outer atmosphere, a thread of memory connecting the Milky Way to its smaller companions. We've mentioned hypervelocity stars, those rogue suns flung from the galaxy at incredible speeds. Let's linger on them a moment longer, because they represent something profound about the galaxy's dynamics. Most stars are gravitationally bound to the Milky Way, trapped by its mass, unable to escape no matter how fast they move. But occasionally, a star reaches escape velocity over 500 kilometers per second relative to the galaxy and is flung outward, never to return. These stars are rare but real. Some are thought to be ejected by interactions with Sagittarius A asterisk, the supermassive black hole at the galaxy center. A binary pair of stars wanders too close. One is captured or consumed. The other is slung outward with tremendous velocity, like a stone from a slingshot. Other hypervelocity stars may be accelerated by supernova explosions in binary systems, by three-body interactions in dense stellar clusters, or by other rare dynamical events. Once free, these stars travel alone into intergalactic space, into the vast darkness between galaxies. They become tiny lighthouses drifting far beyond the spiral's edge, carrying the galaxy's memory outward with them. They will wander forever through that emptiness, isolated, alone, never again to feel the gravity of the Milky Way, never again to pass close to another star. Cosmic exiles, eternal wanderers. There's something both sad and beautiful in that image, isn't there? Freedom and exile, two sides of the same coin, liberated from the galaxy, but also lost to it, free but alone. When a massive star dies and collapses into a neutron star, if the conditions are right, it may be left spinning extremely fast with beams of radiation streaming from its magnetic poles. As the neutron star rotates, these beams sweep across space like the beam from a lighthouse. If the beam happens to point toward Earth at some point in the rotation, we see a pulse of radiation. These objects are called pulsars, and some rotate hundreds of times per second, pulsing with extraordinary regularity. They are so consistent, so precise in their timing, that astronomers use them as cosmic clocks. Pulsar timing can be used to measure distances, test theories of gravity, and even search for gravitational waves passing through the galaxy. Across the Milky Way, pulsars blink quietly, remnants of stellar death, but also beacons of astonishing order. They keep time not for minutes or days, but for entire epochs, ticking steadily in the silence between stars. They are lighthouses in the dark, signals that say something was here, something lived and died and left this behind. They are tombstones and timepieces, endings and instruments, all at once. In the cores of ancient globular clusters, astronomers sometimes find stars that appear too young, too blue, too bright to fit with their surroundings. These globular clusters are billions of years old. All their stars should be old, red, dim. But scattered among the ancient red giants are occasional bright blue stars that look young, as if they formed recently. These are called blue stragglers, and they're not actually young. They're the products of stellar collisions or mergers. In the dense centers of globular clusters, where stars are packed closely together, collisions are rare but possible. When two old stars collide or merge, they can create a single, more massive star that appears younger and bluer than its neighbors. It's been rejuvenated by violence, given a second lease on life through catastrophe. Blue stragglers are stellar phoenixes, reborn from collision, shining more brightly than their age should allow. They're reminders that even in an ancient, settled system, even among the oldest stars in the galaxy, sudden transformation is possible. When clusters of massive stars form together, they live fast and die young. Within just a few million years, they explode as supernovas, often in rapid succession. These sequential explosions create enormous cavities in the interstellar medium. Individual supernova remnants can join together, merging into vast bubbles of hot gas called superbubbles. These can be hundreds of light years across. Some superbubbles punch upward through the galactic disk, creating channels where energy, gas, and magnetic fields escape into the halo. These structures are called chimneys, and they play an important role in regulating the galaxy's structure. They vent pressure from the disk. They redistribute heavy elements created by supernovas. They help shape the halo's structure and content. The galaxy, in this way, breathes not just within the disk, but through these towering columns, carrying energy and matter up and out into the surrounding space. It's a kind of circulation system, a way for the galaxy to regulate itself, to prevent too much pressure from building up in the disk, to distribute material more evenly through its structure. Above and below the Milky Way's bright disk, gas rises and falls in a quiet loop known as the Galactic Fountain. Supernovas and stellar winds heat gas and eject it upward into the halo, where it cools over millions of years. As it cools, it condenses and gently rains back down onto the disk, completing the cycle. This circulation stirs the interstellar medium, redistributes heavy elements, and helps regulate star formation. It's a quiet respiration, a breathing motion of matter between the dense plane and the vast halo. The galaxy doesn't just spin. It circulates, it exhales and inhales, keeping its structure in motion across immense spans of time. This fountain brings freshly created elements from supernova-enriched regions and distributes them more widely through the galaxy. It's one of the mechanisms by which the interstellar medium becomes gradually more metal-rich over time. The Milky Way is not a closed system isolated in space. It draws in fresh gas from the intergalactic medium, from the vast cosmic web that connects all galaxies. Long, tenuous streams of gas flow through this web. Some of these filaments intersect the Milky Way's halo and funnel material inward. This infalling gas provides raw material for new stars, replenishing what the galaxy loses over time to star formation and outflows. Some gas arrives as cold filaments, slipping quietly into the disk without much fanfare. Other streams fall in hotter, shock-heated by their passage through the halo, lighting up in ultraviolet or X-ray wavelengths. These invisible rivers sustain the galaxy's growth and evolution, linking it to the larger universe beyond. The Milky Way is not self-sufficient. It needs this constant inflow to maintain its star formation, to continue growing, to remain vibrant. Even now, the Milky Way drinks from distant reservoirs, nourished by threads of matter spun from the early cosmos, stretched across the void, still feeding galaxies billions of years after the universe began. In 2013, the European Space Agency launched a spacecraft called Gaia with an ambitious mission to create the most precise three-dimensional map of the Milky Way ever made. Gaia measures the positions, motions, and brightness of over 2 billion stars with extraordinary precision. It determines where they are, how fast they're moving, in which directions, and how far away they lie. With each new data release, Gaia has revolutionized our understanding of the galaxy. It has uncovered streams from shredded dwarf galaxies. It has mapped the warp of the disk in detail. It has traced the sun's orbit with exquisite accuracy. It has identified countless binary stars, variable stars, and exotic objects. Gaia has turned the Milky Way from a hazy smear of stars into a sharp, dynamic, three-dimensional structure. We can now see not just where stars are, but where they're going, where they've been, how they move together in groups. It is astronomy's most ambitious star chart, a quiet revolution unfolding among the stars. Future historians of science will likely mark Gaia as a turning point, the moment when we truly began to understand our galaxy's structure and history in detail. Much of the Milky Way is invisible in ordinary light, hidden by dust, distance, or faintness. But radio waves can slip through these barriers, revealing structures otherwise unseen. Radio telescopes trace cold hydrogen gas throughout the galaxy. They outline magnetic fields threading through the interstellar medium. They highlight emissions from pulsars, supernova remnants, and even distant quasars shining through the galaxy from behind. Using arrays of radio telescopes working together, astronomers have mapped the spiral arms, measured the warp of the disk, and discovered star-forming regions cloaked in darkness. Where optical light is blocked, radio wavelengths let us see through, let us perceive structure and motion that would otherwise remain hidden. The galaxy speaks in a language we can't hear with our ears, but one that science has learned to translate into images, into maps, into understanding. Radio astronomy has revealed a Milky Way far more complex and dynamic than what we see with our eyes alone. It's shown us that the galaxy extends far beyond the visible disk, that gas and magnetic fields reach out into the halo, that structure exists in the seemingly empty spaces between stars. Infrared light penetrates dust in ways that visible light cannot. When astronomers began observing the galaxy in infrared wavelengths, they saw through the obscuring clouds and discovered what lay hidden behind them. The Galactic Center, completely blocked in visible light by dense dust clouds, becomes visible in infrared. The central bulge, the bar structure, the dense stellar populations near Sagittarius A*, all revealed when viewed in longer wavelengths. Star-forming regions, dark and invisible in optical images, light up brilliantly in infrared as newborn stars heat the surrounding dust. The warmth of young suns, absorbed and re-radiated as infrared light, shows us where stars are being born right now. Infrared surveys have mapped the galaxy's structure in unprecedented detail, showing us the three-dimensional arrangement of stars, gas, and dust. They've revealed populations of cool red dwarfs, the most common type of star but too faint to see easily in visible light. They've shown us brown dwarfs, objects too small to be stars but too large to be planets, drifting unseen through the darkness. The Milky Way in infrared is a different galaxy than the one we see with our eyes. Warmer, glowing with hidden heat, full of structure that visible light misses entirely. Certain stars pulse in brightness over regular intervals, expanding and contracting like slow, luminous heartbeats. These are variable stars, and some types have a remarkably useful property. Cepheid variables and RR Lyrae stars have well-known relationships between their true brightness and their pulse period. By measuring how long a star takes to brighten and dim, astronomers can determine its actual luminosity. And by comparing that to how bright it appears from Earth, they can calculate its distance. These stars serve as cosmic yardsticks, helping us map the shape, structure, and scale of the Milky Way. They are lights that measure the dark, blinking beacons scattered through the spiral, each one a distance marker, helping us understand the galaxy's true dimensions. Without variable stars, we would have a much harder time determining distances within the galaxy. They provide a reliable, consistent method for measuring how far away things are, which is one of the most fundamental and difficult problems in astronomy. Though the Milky Way appears calm in visible light, it glows fiercely in other wavelengths. X-rays pour from the Galactic Center, from collapsed stellar remnants, from the edges of black holes where matter heats to millions of degrees. White dwarfs and neutron stars in binary systems can siphon matter from companion stars. As this stolen material spirals inward, it heats to extreme temperatures and emits X-rays. These systems are called X-ray binaries, and they dot the galaxy, invisible to optical telescopes but brilliant in X-ray wavelengths. Hot gas in the halo also emits faint X-rays, revealing the galaxy's larger skeleton, the structure of the halo, and the distribution of hot plasma. Supernova remnants glow in X-rays as shock waves heat surrounding gas to millions of degrees. Telescopes like Chandra and XMM Newton have painted a very different portrait of the galaxy than what we see with our eyes. Not a tranquil spiral, but a realm of extreme temperatures, compact remnants, violent accretion, and hidden radiation. The X-ray Milky Way is a galaxy of high energies, of matter under extreme conditions, of processes invisible to human eyes but absolutely real, absolutely happening all around us. In about 4.5 billion years, the Milky Way and Andromeda will collide. But the process won't be instantaneous. It will unfold over billions of years in a slow, complex dance. First approach will happen in about 4 billion years. The two galaxies will swing past each other, their gravity warping both structures, pulling out tidal tails, disturbing star orbits, but they won't merge on the first pass. They'll swing apart again, each distorted by the encounter. Then gravity will pull them back together. They'll approach again, swing past again, losing energy with each passage. Over billions of years, they'll gradually spiral closer, their structures becoming more and more disrupted, their shapes less and less recognizable. Eventually, they'll merge into a single system. The spiral structures will be destroyed. The combined galaxy will likely settle into an elliptical shape, a vast collection of stars in random orbits, rather than the organized disk and arms we know today. The supermassive black holes at the center of each galaxy, Sagittarius A and Andromeda's central black hole, will spiral together and eventually merge into a single, more massive black hole. This merger will release gravitational waves that will ripple across the universe. Our solar system, if it still exists, will likely survive the merger. Stars almost never collide directly. The distances are too vast. But we'll be relocated, moved to a different part of the merged galaxy, seeing an entirely different sky, different stars as neighbors. It will be a slow, elegant transformation. The future written in gravity and time. After the Andromeda merger is complete, after the combined galaxy settles into its new configuration, what then? What is the ultimate fate of the Milky Way? Over trillions of years, star formation will gradually cease. The gas needed to make new stars will be used up or expelled. The galaxy will slowly grow darker as stars age and die without being replaced. The longest-lived stars, the tiny red dwarfs, can burn for trillions of years. The universe is not yet old enough for any red dwarf to have reached the end of its natural lifespan. But eventually, even they will exhaust their fuel and fade. As stars die, they'll leave behind white dwarfs, neutron stars, and black holes. The galaxy will become a collection of stellar remnants, cold and dark, drifting through space. Over even longer timescales, the galaxy itself may begin to evaporate. Close encounters between stars can occasionally give one star enough energy to escape the galaxy entirely. Over astronomical lengths of time, the galaxy could slowly lose stars this way, gradually dissolving. Eventually, in the truly distant future, the universe may be dominated by isolated black holes, drifting alone through an expanding, cooling, darkening cosmos. Even the black holes will eventually evaporate through Hawking radiation, though this process takes unimaginably long periods. But this is so far in the future, so many orders of magnitude beyond human timescales, that it becomes abstract. The galaxy has many billions of years of life ahead of it, many epochs of star formation, many generations of stellar evolution. For now, the Milky Way is alive, vibrant, still making stars, still evolving, still beautiful. Long before the galaxy faces its ultimate fate, our own sun will die. In about 5 billion years, the sun will exhaust the hydrogen in its core and begin to expand into a red giant. As it swells, it will likely engulf Mercury and Venus. Earth may be swallowed as well, or it may survive but be scorched to a lifeless cinder by the intense heat. Either way, Earth as we know it will be destroyed. The sun will shed its outer layers in a planetary nebula, a beautiful shell of glowing gas expanding into space. At the center, the sun's core will remain as a white dwarf, a dense hot remnant about the size of Earth, but with about half the sun's current mass. This white dwarf will slowly cool over billions of years, gradually fading from white to yellow to red to brown to black. Eventually, it will become a black dwarf, a cold, dark stellar corpse drifting through space. But this happens long before the Andromeda merger is complete. The sun's death and Earth's destruction will occur while the Milky Way is still a spiral, still recognizably itself. Any descendants of humanity, if they still exist, will need to have moved to other star systems long before the sun dies. They'll need to have spread throughout the galaxy, or beyond, to survive as a species. Or perhaps they'll have transformed into something we wouldn't recognize, something adapted to life in space, no longer dependent on planets or stars. Who can say what humanity or its descendants might become over such vast timescales? If the galaxy is so vast, so full of stars and planets, where is everyone? This question, first posed by physicist Enrico Fermi, has become known as the Fermi paradox. The Milky Way is about 13 billion years old. It contains hundreds of billions of stars. Many of those stars have planets. Some of those planets are likely habitable. Even if intelligent life is rare, there's been enough time and enough opportunities for it to arise many times. If intelligent life exists elsewhere, some civilizations might be millions or even billions of years more advanced than us. They would have had time to spread throughout the galaxy, to leave detectable signs of their presence. And yet we see nothing. No signals. No evidence of megastructures. No signs of galactic-scale engineering. The galaxy appears empty of other intelligences, or at least, they're not making themselves obvious to us. This is the paradox. The apparent contradiction between the high probability of extraterrestrial life and the complete absence of evidence for it. There are many proposed solutions. Perhaps intelligent life is extremely rare. Perhaps we're the first in our galaxy. Perhaps intelligence tends to destroy itself before spreading very far. Perhaps civilizations are common, but they hide, or they don't expand aggressively, or they communicate in ways we haven't thought to look for. Or perhaps we're simply too young, looking in the wrong places, at the wrong times, with the wrong methods. The universe is vast, and we've barely begun to search. The question remains open, the paradox unresolved. Are we alone in the Milky Way? Or are we surrounded by others who remain, for whatever reason, undetected? Planets are not a rare feature of the cosmos. They're a natural consequence of star formation, and they exist throughout the Milky Way in enormous numbers. As a new star ignites, a rotating disk of leftover gas and dust surrounds it. Within this disk, particles collide and stick together, gradually accumulating mass and growing into planets. The process is inevitable, happening around most stars. We've discovered thousands of exoplanets, planets orbiting other stars, and we've barely scratched the surface. Based on current surveys, astronomers estimate there may be more planets than stars in the galaxy. Perhaps hundreds of billions of worlds. Some are vast gas giants larger than Jupiter. Others are rocky worlds similar to Earth. Some orbit close to their stars, scorched and tidally locked. Others drift in cold outer regions, frozen and dark. Some may have water oceans, thick atmospheres, conditions suitable for life. The diversity is astonishing. We found planets orbiting binary stars, planets orbiting pulsars, planets drifting alone through space with no star at all. Hot Jupiters, super-Earths, mini-Neptunes, lava worlds, ice worlds, planets we never imagined before we started looking. The galaxy is not just full of stars, it's full of worlds, full of systems, each one unique, each one with its own story, its own conditions, its own potential. Within the clouds of interstellar dust that drift between stars, scientists have detected complex organic molecules, carbon-based compounds that form the raw ingredients for life. These include polycyclic aromatic hydrocarbons, molecules made of carbon rings linked together. Simple sugars, amino acids, alcohols, and other organic compounds have been found in comets, meteorites, and interstellar clouds. Though not alive, these molecules are chemically rich, formed in the atmospheres of dying stars or within cold clouds shaped by ultraviolet radiation and cosmic rays. They represent a kind of pre-biological chemistry, the building blocks that, under the right conditions, might eventually lead to life. These tiny grains are carried across light years by galactic winds and stellar radiation. They settle into the gas that forms new stars and planets. Some may have fallen onto the early Earth, delivering organic compounds from space. The galaxy's dust is not just debris. It's cargo, potential, the seeds of complexity drifting silently through the dark. The chemistry of life may be common throughout the galaxy, scattered widely, waiting for the right conditions to spark into something more. In 1961, astronomer Frank Drake proposed an equation to estimate the number of detectable civilizations in the Milky Way. It's not meant to give a precise answer, but to organize our thinking about the factors involved. The equation multiplies together several terms: the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, the fraction where life actually arises, the fraction where life becomes intelligent, the fraction that develops detectable technology, and the length of time such civilizations remain detectable. The problem is that most of these numbers are unknown. We can estimate star formation rates and planet frequencies reasonably well, but we have no idea how often life arises, or how often it becomes intelligent, or how long civilizations typically last. Depending on which numbers you plug in, the Drake equation can suggest anything from "we're alone in the galaxy" to "there should be millions of civilizations out there." It's less an equation than a framework for thinking about the question. What do we need to know to answer whether we're alone? Which factors are most important? Where should we focus our search? The equation itself doesn't answer the question, but it helps us understand what questions we need to answer. Let's take a moment to consider where we are, our full cosmic address, starting small and zooming out. You are on Earth, a rocky planet orbiting an average star called the Sun. The Sun is one of hundreds of billions of stars in the Milky Way galaxy. The Milky Way is a spiral galaxy, part of a small collection called the Local Group, which includes about 50 galaxies. The Local Group is part of the larger Virgo supercluster, a vast collection of galaxy clusters. And the Virgo supercluster is just one small region of the observable universe, which contains hundreds of billions of galaxies. Each level represents an increase in scale so dramatic, it's hard to comprehend. From person to planet to solar system to galaxy cluster to supercluster to observable universe. Each step is orders of magnitude larger than the last. And yet the observable universe is not the entire universe. It's just the part we can see, limited by the speed of light and the age of the cosmos. Beyond the observable edge, the universe likely continues, perhaps infinitely. Our cosmic address places us in a specific location, but also reveals just how small that location is, how insignificant in the grand scale of things. And yet, paradoxically, that's where everything we know exists. All human history, all life on Earth, all our triumphs and tragedies, confined to one small planet orbiting an average star in the outer suburbs of an ordinary galaxy. There's something both humbling and comforting in that perspective. Our problems, our anxieties, our worries, they matter to us absolutely. But in the cosmic scale, they're vanishingly small. Perhaps there's peace in that realization. In 1990, as the Voyager 1 spacecraft was leaving the solar system, astronomer Carl Sagan convinced NASA to turn its camera around and take one last picture of Earth from the edge of the solar system. In that image, Earth appears as a tiny point of light, less than a single pixel, a pale blue dot suspended in a beam of scattered sunlight. From that distance, about 6 billion kilometers away, Earth is barely visible, one small world among the stars. Sagan wrote beautifully about that image. He noted that everyone you love, everyone you know, everyone you've ever heard of, every human being who has ever existed, lived out their lives on that tiny mote of dust. Every war, every discovery, every act of kindness or cruelty, all happening on that pale blue dot, and that's just from the edge of our solar system. From the nearest star, Earth would be completely invisible, lost in the glare of the sun. From across the galaxy, our entire solar system is just one star among hundreds of billions, utterly unremarkable. This perspective can feel crushing, overwhelming, can make us feel insignificant and small. But it can also be liberating. It can remind us that our differences are petty, that our conflicts are temporary, that we're all in this together on this one small world. Sagan called Earth the only home we've ever known and urged us to cherish it, to be kinder to one another, to preserve and protect this pale blue dot for future generations. Let's think about time for a moment. Deep time. Cosmic time. Timescales so vast they become difficult to comprehend. The universe is about 13.8 billion years old. The Milky Way formed shortly after, about 13 billion years ago. Our solar system is 4.6 billion years old, about a third the age of the universe. Earth formed at the same time, cooling from a molten ball into a world with liquid oceans within a few 100 million years. Life arose surprisingly quickly after that, at least 3.5 billion years ago, perhaps earlier. For most of Earth's history, life was single-celled, simple, microscopic. Complex multicellular life only appeared in the last billion years or so. Animals with hard shells, the first fossils we easily recognize, only appeared about 540 million years ago in the Cambrian explosion. Dinosaurs ruled the Earth from about 230 million years ago until 66 million years ago, a reign that lasted over 160 million years. By comparison, humans have existed for perhaps 300,000 years. Civilization, cities, writing, all emerged in just the last 10,000 years. All of recorded history, everything from ancient Egypt to the present day, spans about 5,000 years. A blink of an eye in geological time, essentially instantaneous on cosmic scales. We live in a thin slice of time, an infinitesimally small moment in the vast history of the cosmos. And yet, this is our moment. This is when we exist. This brief window is when consciousness, At least our consciousness gets to witness the universe, to contemplate its nature, to feel wonder at its vastness. Here's a fact worth contemplating as you drift towards sleep. You are made of stardust. Not metaphorically, but literally, physically, you are composed of atoms that were forged in the hearts of stars. The hydrogen in your body, the simplest element, was created in the Big Bang. But everything else, every other atom, was created in stars. Carbon in stellar cores, nitrogen and oxygen in dying red giants, iron in supernova explosions. When stars die, they scatter these elements into space. Over billions of years, this enriched material mixes, accumulates, forms new clouds of gas and dust. And from those clouds, new stars and planets are born, carrying with them the legacy of previous generations. The atoms in your body have a history. They were created billions of years ago in stars that no longer exist. They drifted through space, were incorporated into the molecular cloud that formed the Sun and Solar System, condensed into the rocky material that became Earth. For billions of years, they resided in the Earth, in rocks, in the ocean, in the atmosphere. Eventually, they became part of living organisms, passing through the biosphere, cycling through countless life forms before ending up in you. Every atom has a story, a journey that spans billions of years and unimaginable distances. You are not separate from the cosmos. You are part of it, intimately connected to stars and galaxies, composed of the same matter, following the same laws, part of the same grand story. And when you die, those atoms will return to the Earth, will eventually be recycled, will continue their journey. Nothing is lost. Everything transforms. The cycle continues. Throughout this journey, we've encountered many mysteries. Things we don't fully understand, questions we haven't answered. And that's appropriate, because mystery is a fundamental part of the universe. We don't know what dark matter is. We don't know if we're alone in the galaxy. We don't fully understand how the spiral arms maintain their structure. We're not certain about the Milky Way's exact mass. We don't know what happens inside black holes. These aren't failures of science. They're the frontier, the edge of knowledge where discovery happens. Every answered question reveals new questions. Every solved mystery opens doors to deeper mysteries. And that's beautiful. That's something to celebrate rather than lament. A universe that was fully understood, completely mapped, entirely known, would be smaller somehow, less wondrous, less capable of inspiring awe. The mysteries keep us humble. They remind us that human knowledge, vast as it has become, is still limited, still surrounded by unknowns. There is always more to discover, always deeper to dig, always further to explore. We've talked about the future of the galaxy, the eventual merger with Andromeda, the slow decline of star formation over trillions of years. But these are projections based on our current understanding. The actual future might be very different. We don't know what technology future civilizations might develop. We don't know if intelligent life will spread throughout the galaxy, fundamentally altering its evolution. We don't know if our understanding of physics is complete, or if we'll discover new laws, new forces, new possibilities. The future is unwritten, unknown, full of potential. And that's not something to fear, but something to embrace. The universe is still young, the story is still unfolding. Anything might happen. Perhaps life will spread from star to star, filling the galaxy with consciousness, transforming dead worlds into living ones. Perhaps intelligence will find ways to transcend the physical limitations we currently accept, to exist in forms we can't imagine, to survive long after biological life is no longer possible. Or perhaps the galaxy will remain mostly empty, mostly dark, with scattered islands of life existing briefly before fading back into the cosmic night. We don't know. We can't know. The future remains open, undefined, full of possibility. Here's something remarkable. For most of cosmic history, the universe existed without being observed, without being understood, without being appreciated. Stars formed and died without anyone watching. Galaxies collided without witnesses. The cosmos unfolded in darkness and silence, its beauty unseen, its complexity uncomprehended. But now, in at least one small corner of one galaxy, the universe has become aware of itself. Matter has organized itself into complex structures capable of reflection, of study, of wonder. We are the universe contemplating itself, cosmic material become conscious, atoms arranged in patterns capable of understanding their own origins. That's extraordinary. That's a privilege, a gift, something precious and rare. Consciousness, awareness, the ability to look up at the night sky and wonder what those lights are, where they came from, what they mean. You have that gift. Right now, lying here, drifting towards sleep, you are part of that cosmic self-awareness. You are matter that knows its matter, stardust that can contemplate its origins, a temporary pattern of atoms capable of wonder. And perhaps that's enough. Perhaps the meaning of existence is not something external, something imposed from outside, but simply this, the universe experiencing itself, matter becoming aware, the cosmos knowing itself through us. We've traveled far tonight, from the galactic halo to the central black hole, from ancient stars older than the galaxy to stellar nurseries where new suns are being born. We've considered dark matter and spiral arms, collisions and mergers, past and future. But through it all, there's been a constant thread. Change. Motion. Transformation. Nothing in the galaxy is static or permanent. Everything flows, shifts, evolves. Stars are born and die. Galaxies collide and merge. Matter cycles through generations, transforming from one form to another. And in this endless transformation, there is something beautiful. The universe is not a finished product, not a static creation, but an ongoing process. It's still becoming, still evolving, still creating new forms and structures. You are part of that process. Not separate from it, not outside observing, but intimately involved, fundamentally connected. The atoms in your body have been on this journey for billions of years, cycling through stars and space and now, temporarily, forming you. When we feel overwhelmed by our daily concerns, by the demands of life, by the weight of our responsibilities and worries, it can help to zoom out, to gain cosmic perspective. Your problems are real. Your struggles matter. But they're also temporary, confined to this brief moment, this small planet, this thin slice of time. In the vast sweep of cosmic history, your anxieties are fleeting. That's not meant to diminish your experience or invalidate your feelings. It's meant to provide relief, to offer perspective, to remind you that things pass, that change is constant, that nothing lasts forever, good or bad. The galaxy turns on. Stars continue their orbits. The cosmic dance proceeds regardless of our individual concerns, and there's something comforting in that continuity, in knowing that the universe is larger than our problems, that existence continues beyond our brief struggles. You are small, but you are part of something vast. Your life is brief, but you are connected to something eternal. You are insignificant in the cosmic scale, but you are made of the same matter as stars, following the same laws, part of the same grand pattern. Here's a paradox to rest with. Everything in the galaxy is in motion. And yet, from our perspective, everything appears still. Stars orbit but seem fixed in place. The galaxy rotates but appears unchanging. The universe expands but looks static, all because the timescales are so vast, the motions so slow, that from our brief perspective, they appear as stillness. And perhaps there's wisdom in that. Perhaps we can learn to find stillness even in motion, peace even in change. The universe teaches us that you can be moving and still at rest, changing and yet constant, flowing and yet centered. As you lie here, your body is completely still, at rest, relaxing deeper with each breath. And yet you're moving at tremendous speeds. The Earth rotates. The planet orbits the Sun. The solar system sweeps through the galaxy. The galaxy moves through space. You are simultaneously still and in motion, at rest and traveling. Both are true. Both are real. Stillness and motion, change and constancy, together, always, inseparable. Let's return to something simple now. Something immediate and present. Your breath. Feel the gentle rise and fall of your chest. The slow rhythm of inhalation and exhalation. Air flowing in, air flowing out. The most basic process of life, the constant exchange of gases that keeps you alive. That air contains oxygen created billions of years ago in dying stars. That oxygen enters your lungs, diffuses into your blood, travels to your cells where it enables the chemical reactions that power your body. And then you exhale carbon dioxide, releasing it back into the atmosphere. You are part of the cosmic cycle of matter, breathing in stardust, breathing out the products of cellular metabolism. Connected to the galaxy through each breath, through the atoms that pass through your body, through the energy that powers your existence. Everything is connected. Everything flows. Everything transforms. And you are part of it all, intimately, fundamentally, eternally. As you sink deeper into relaxation, as sleep approaches, let go of the details. Let go of the facts and figures. Let go of trying to remember or understand everything you've heard tonight. None of it needs to be held onto. It's enough to have listened, to have contemplated, to have opened your mind to these vast perspectives. The specific information doesn't matter as much as the feeling, the sense of wonder, the reminder of how large and strange and beautiful the universe is. Let it all drift away like stars disappearing in morning light. Let your thoughts become slower, softer, quieter. Feel yourself floating in a vast darkness, surrounded by distant lights, safe and small, and part of something infinite. There's nothing you need to do, nothing you need to remember, nothing you need to figure out or understand or solve. Just rest. Just breathe. Just be. Sleep is your nightly return to the cosmic darkness from which you came. A temporary dissolution of consciousness, a brief surrender of the self, a small death and rebirth that happens every night. In sleep, your busy mind quiets. Your anxious thoughts dissolve. Your body repairs and restores itself. You let go of waking concerns and drift into a state closer to the vast unconsciousness of the cosmos. And that's not something to fear, but something to embrace. Sleep is a gift, a necessary rest, a chance to stop doing and simply be. It's your connection to the great stillness that exists beneath all motion, the silence beneath all sound, the darkness from which light emerges. Let yourself sink into that darkness now. Let go of staying awake. Release your hold on consciousness. Allow sleep to take you gently, peacefully, naturally. You are safe. You are small. You are part of something vast and ancient and ongoing. The galaxy turns, stars orbit. The cosmic dance continues. And you can rest, knowing that you are held in the gravity of existence, that you belong here, that you are home. The stars are dimming now behind your closed eyes. The journey through the Milky Way is complete. You've wandered through stellar nurseries and ancient star clusters, past black holes and supernova remnants, through dust clouds and spiral arms. You've heard of collisions and mergers, of dark matter and hypervelocity stars, of galaxies being torn apart and new stars being born. You've contemplated timescales that span billions of years and distances that stretch across hundreds of thousands of light years. But most importantly, you've found a place to rest. Your mind has had something gentle to focus on, something vast and peaceful to contemplate as you drift away from the concerns of the day and toward the quiet darkness of sleep. Remember that you are part of this galaxy, not just living in it, but made from it, connected to it, inseparable from it. The iron in your blood was forged in stars. The oxygen you breathe was created by stellar fusion. The atoms of your body have been on a journey for billions of years, and they will continue that journey long after you're gone. You are stardust, briefly conscious, temporarily organized into a pattern capable of wonder. And tonight, you've used that consciousness to contemplate the cosmic home from which you came and to which you will eventually return. But for now, simply rest. Let sleep take you gently into its embrace. Let your breathing slow. Let your muscles relax completely. Let your thoughts dissolve like morning mist. The Milky Way continues its slow rotation. Stars orbit in their ancient paths. Somewhere, a new sun is being born in a cloud of dust and gas. Somewhere, an old star is dying, scattering its enriched material back into space. The cycle continues, as it has for billions of years, as it will for billions more. And you are part of that cycle. Resting now, but connected always, a small warmth in the cosmic dark, a brief flicker of consciousness in the vast night. Sleep well, traveler, dream softly, and know that when you wake, the galaxy will still be here, still turning, still carrying you through space on your journey around the Galactic Center. May you find peace in the vastness. May you rest in the darkness between stars. May you sleep deeply, knowing you are home. Good night.